y equals x to the power of n, where n is some real number. The derivative dy dx is given by nx to the power of n minus 1. So we just multiply in front by the power and subtract 1 from the power. So as usual, we use Newton's quotient. F of x equals x to the power of n. And here's Newton's quotient. So f of x plus h is x plus h to the power of n minus f of x, which is x to the power of n, divided by h. Now I'm going to use the binomial theorem to expand out x plus h to the power of n. Now I just want to remind you about the binomial theorem. It's called a binomial because we have two nomials. Bi meaning two, nomial meaning term. Two nomials are two terms raised to a power. So in general, it's a plus b to the power of n. So what we do is we start off with nc0, so these are combinations. And we keep on increasing this number here. So we have nc0, then we have nc1, then we have nc2, and so on. If n is a positive integer, this series will terminate with ncn. It'll actually terminate with ncn, a to the power of 0, b to the power of n. That's if n is an element of capital N. That means if n is a positive integer. But if n is not a positive integer, if n is a fraction, then we'll have an infinite series. So in general, n will not be a positive integer. N will be any real number. So we won't have a final term in general. So we'll have an infinite series. So I want to apply it to x plus h to the power of n. So x takes the place of a, h takes the place of b. So we're going to have nc0 times x, which is a, to the power of n, times b, which is h, to the power of 0, plus the next term is nc1 times a, which is x. Now we decrease the power of a by 1. So we are x by 1. So we have x to the power of n here. We'll have x to the power of n minus 1 here. And we increase the power of b. So 0, 1, 2. You see the powers of b are increasing. So b is h here. h to the power of 1 plus nc2 x to the power of n minus 2 times h squared, etc. Plus dot dot dot. And all of this is divided by h. Now we have to take the limit as h tends towards 0. We have to take the limit as h tends towards 0 of Newton's quotient. Something I forgot to mention is that we have to subtract x to the power of n. Okay, I forgot this. So we have an infinite series here. If, as I explained, if n is not an integer, we'll have an infinite series in the binomial expansion of x plus h to the power of n. And then we subtract x of n. And then we divide the whole lot by h. Now let's simplify this a bit further. nc0 is just 1 times x to the power of n times h to the power of 0. So that's just going to be x to the power of n. So this first term is x to the power of n, because h to the 0 is 1. nc1 is n times x to the power of n minus 1 times h. nc2 is n times n minus 1 divided by 2 factorial times x to the power of n minus 2. And then we have h squared. Okay, nc2, we just multiply n by 1 less than n, and we divide by the number of terms we have on top, which is 2 terms. So we 2 factorial in the denominator, and etc. I'm not going to write it all out because you see that we don't need to write it all out. We have to subtract x to the power of n, and then we just divide all of this by h. See that x to the power of, we have plus x to the power of n here, and we have minus x to the power of n. That's that minus x to the n. They cancel out. And if we divide this by h, the first term divided by h gives us nx to the power of n minus 1. Okay, the h is cancelled there for the first term. When we divide the second term by h, we get plus n times n minus 1 over 2 factorial times x to the n minus 2 times h. Now the next term will involve h cubed, okay, because the powers of h are increasing, as I said to you already. So h to 0, h to 1, h squared, h cubed. So the next term will involve h cubed over h. So we'll get h squared in it. So all these terms here after this one will involve increasing powers of h. So we needn't worry about them because we're going to take the limit as h tends to 0 of Newton's quotient. That's our derivative. And when we do that, this will go to 0. Everything will go to 0. We'll just be left with nx to the power of n minus 1. That's what we had to prove. This is the derivative.